The rest of section 1, physics 121. So just before the break, the virtual break in our virtual class here, I had said that if you have motion with a constant acceleration, this little group of 5 equations will apply. If the acceleration changes, then most of them become invalid. So you want to be careful of that in other types of situations. But I'm going to run through a couple of examples that you can sort of imitate when you do some. So at least in this older version, I called this 1B. It's the question about the rock being dropped off the cliff. Okay, you're visiting, I don't know, some national park or something like that, and you're standing on the edge of this beautiful vista where you're up high on some cliff, and you're saying to yourself, I wonder how far down it is. And you don't happen to have a tape measure several hundred feet long with you that you can just lower down. So you decide to drop a rock and time it, which might not actually be the best possible idea. If there's hikers down there, you could hurt somebody. But, well, be that as it may. If the thing falls for 5 seconds before it hits bottom, how high up are you is the question. So before worrying about the answer, the first thing is to figure out what the question is, okay? If we're going to break this down into a step-by-step, do this first and then do that kind of a recipe, step 1, oh, he's writing in cursive again. It's just printing is so slow. Rephrase the question in terms of X, T, etc. So basically, you need to translate the question from from English into math. Okay. At least for people who are just starting out, I recommend actually doing this on paper instead of trying to do everything in your head. The more step-by-step and methodical you are about how you approach problems, the higher your chance of success. Take a big problem and divide it up into smaller, easier pieces. So step 1, make a list. What are you given? In other words, what do you know as you start out? And what are you trying to find? So read back through the question and think about what each little piece of it is telling you. You drop a rock. The word drop is significant because you didn't throw it, you simply released it. So as it left your hand, its velocity was 0. That's telling you the initial velocity, the velocity at the beginning of its descent. V initial equals 0. Okay, what else do we know? See it hit bottom 5 seconds later. Well, 5 seconds is the time. You can tell because it's measured in seconds. Don't underestimate the importance of looking at the units on things. So T for time. 5.0 S for seconds. How high is the cliff? Well, the height of the cliff would be the same thing as the distance moved by the rock. And the distance moved by the rock is delta x, the displacement of the rock, how far from where it started to where it ended up. This by itself is not enough information to solve the problem, but you start out knowing something else also, even though the question doesn't explicitly mention it to you. You know the rate that this rock is gaining speed. So to the extent you can assume it's a freely falling object, and that's not too bad of an assumption for a heavy something heavy falling for 5 seconds. It might be starting to slow down a little bit the last second or two, but to a decent approximation, we can say that A is equal to G, where you see this rate of acceleration comes up so often, it's given a name of it, its own symbol, G for the gravitational acceleration, the acceleration due to gravity. So since it's a free-falling object, its acceleration is equal to G, which, as everybody knows, near the surface of the Earth, it's 9.8 meters per second. Now, basically what that number is it's how we describe the strength of the gravitational field you're in. If you're on Mars, that's something like 3.7 or 3.8, or I'd have to look it up exactly, but it's roughly a third of what we have on Earth if you're on Mars. And actually, even on Earth, it varies a little bit depending on exactly where you are. If you go to the next decimal place, it's anywhere from about 9.78 to 9.83, depending on your latitude and your altitude and some other less, some minor factors also. But locally here in Batavia, it is just about 9.80, 9.803 or 9, something in that neighborhood. So we'll use 9.8 because that's actually, locally, that's good to 3 digits. The mean value for the planet as a whole is about 9.81, but locally 9.80 is a little closer. So now that we've included that, this is everything we start out knowing. This is what we're looking for. And then what you want to do, you know what, I should have the actual formula sheet. Let me pause this yet again and figure out where the heck I put that. Well, either I don't have a copy of the formula sheet here at home with me, or I've managed to hide it from myself pretty effectively. Either one of those things is believable. This is the formula sheet for Physics 131, which starts out pretty similar looking. So anyhow, the idea is, if you're in the middle of a test, you've got this list of equations that describes motion with a constant acceleration. And which one do you pick? Well, you pick the one that contains just the things on the list you just made. That's one of the reasons for making the list. So for example, the first one, V average, and there's nothing here that's V average. The second one, where we're trying to find delta x isn't in this one. Over here, there again, doesn't contain the thing we're looking for. So you go along like that, and the problem here is it's got V final in it. V final isn't on the list anywhere, but this guy over here, delta x, vi, t, and a, those are the things I've written down here. I know everything in this equation except for delta x, and delta x is the thing I'm looking for. So that's why I select this one. Okay, so step 2. Select equations. Well, equation or equations. If you're lucky, you can find one equation that'll take you right straight to the answer in one step. More often than not, that's what'll happen. Once in a while, you might have to do one of these things where you use this equation to find something which you then put in the other equation and get the answer. But so select equations, and what you keep in mind as you're doing the selecting look for an equation containing just these things. It's probably a good idea for you to take notes, by the way. If you don't already have this question all figured out on your own, treat it just like you're really in class. Take notes. So anyhow, the equation that fits this description this time, V initial t plus 1/2 at squared. And then finally, fill in the numbers and solve it. Solve. Delta x equals, V initial is 0. I suppose I could write 0 times 5 seconds, but, well, that's obviously going to equal 0, so I might as well just write 0. 1/2 9.8 times 5 squared equals 122 meters. This is like roughly 400 feet, maybe a little less. Okay, so I'll run through one more and then have you work on some stuff. Next question, the one with the rocket. Calculation's pretty straightforward on this one. My main thing is I want to talk some more about units, but as far as the actual question, it tells you, now this time it's not a freely falling object, so the acceleration does not equal 9.8, rather it's 25 this time as the rocket gains speed. Maintains this for 2 minutes, and then I suppose that's when it runs out of fuel. So what final speed does it reach when the engine cuts out is the question. To set it up, start out the same way. Given. And what are you trying to find? Maintains an acceleration of 25. Okay, so that's telling you the acceleration. A equals 25 meters per second per second. A rocket maintains an acceleration of 25 meters per second squared for 2 minutes. Time equals 2 minutes. What is its final speed? Final speed. Find V final. What is its final speed if it started from rest? Started from rest is telling you V initial equals 0. Okay, so get it all laid out nice and neat in front of you. What do you start out knowing? What is it that you're looking for? And next step, you go to the formula sheet, try and find an equation containing just these 4 things, which this time would be V final equals V initial plus AT. Fill in the numbers. 0 for V initial, acceleration 25 meters per second squared. Now, I'm just going to put it in exactly the way it was given in the question, where it said the time was 2 minutes. And my point here is that using inconsistent units is one of the more common thing. See, I've got this one. This is the red one. This one is not your friend. Okay? You want that to stay away from your papers. And one of the more common reasons for this to come out and do its dirty deeds is inconsistent units, like seconds here and minutes there. So the answer is not 25 times 2 equals 50. That's wrong. People do it all the time. Try not to be one of them. Inconsistent units, that's worth about 3 exclamation points. Seconds here has to match up with seconds there. Or you could do it the other way around and have minutes here, but that would be kind of unconventional. Now, people are pretty familiar with minutes and seconds, and you can probably figure out that I should have 120 seconds there. But let me go through kind of a step-by-step methodical way of doing it, because that way you're all set up for other things that are less familiar, like if you're converting watts into, if you go into the formula sheet. Where did I put the formula sheet this time? Later in the course, we'll be talking about power, okay? The last page of the formula sheet is all about units. And there's all sorts of useful conversion factors here, and you've got the SI prefixes. And I think it's laid out the same way on the one for your course. But, you know, it says right here that 1 horsepower is a little under 746 watts. Well, the trick is, if you're in the middle of some problem and you have to convert from horsepower into watts or watts into horsepower, should you be multiplying by 746 or should you be dividing by it? And you do that by canceling out units. Back again to that idea that units obey the same algebraic rules that numbers do. So I mentioned before about how that if you multiply something where the top equals the bottom, like multiplying by, I don't know, 5 over 5, that you still got the same thing. If the numerator equals the denominator, the top equals the bottom, if you multiply by something where the top is equal to the bottom, you've got the same thing when you're done. This is still true in a sense. Like so. Still true in a sense, like so. If you take your 2 minutes and multiply by 60 seconds over 1 minute. 60 seconds equals 1 minute, right? So I'm multiplying by a fraction where the numerator equals the denominator. Of course, they're not numerically equal, so I'm not going to have the same number when I'm done, but they are physically equal. This and this mean the same amount of time. You set up this fraction so that the unwanted unit cancels out. Minutes divided by minutes goes away, leaving you with seconds, 120 of them. So that's how you can figure out that you ought to be multiplying by 60, not dividing. If you did it the other way around, you'd have, instead of seconds, you'd have square minutes per second, which is definitely not what you want. Okay, so it's the same if you're converting watts into horsepower or degrees into radians or whatever it is that needs converting, multiply by a fraction where the top is equal to the bottom, set up in a way that makes the unwanted units cancel each other. And that's how you figure out if you should be multiplying or dividing by that conversion factor that you can just look up in the formula sheet. So I should probably label things here. Cancel the units as if they were numbers, and you're left with seconds. Okay, so back at the problem with the rocket, the final equals 25 meters per second squared times 120 seconds. I see seconds here cancels with one of the seconds there. So as far as the units, it'll come out in meters per second. The velocity has a unit of velocity on it, which is what's supposed to happen. And 25 times 120 is 3,000. Okay, so what's left is some examples for you to try. Number 3 is basically an exercise in this sort of converting units that I was just talking about. 4 and 5 are, you know, kind of like the other one that I did, sort of, a little bit. Pause it here. When you unpause it, I'll go over number 3 and say another couple of things before we go on to number 4. Okay. How I did well, it's number 3 on, again, I'm not sure. I may have renumbered the problems a little differently if I'm thinking of the right course, but whatever I called it on the version of the notes that you're working from, the question is to convert 50 miles per hour into meters per minute. So maybe I'll just, instead of writing it all out, maybe I'll just lay this thing there where it's already written out. There's actually more than one way of doing this. First way that came to my mind is you go to the last page of the formula sheet where you can look up the conversion factors like I showed you, and it says there that 1 mile, when rounded off to the nearest meter anyhow, it's 1,609 meters. So this equals that. Since, you know what, I should work through this a step at a time so you can kind of see it unfolding in front of your eyes rather than just plop, here's the answer. So number 3, or at least what was called number 3 last year, you got 50 miles per hour. Before you even worry about filling in any numbers, maybe the place to start is that since miles is on top in miles per hour, you want miles to be on the bottom in this. And what you want to convert into is meters. And then you go look it up, and it says 1 mile equals 1609 meters. Miles will cancel miles, and now you've got meters, which is part of what you wanted. The other thing you want in your answer is seconds. So another fraction where the top equals the bottom to clean up the unit of time. Since hours is on the bottom in miles per hour, you want hours on top in this fraction. And what you want to convert it into is, let's see, actually it asks for miles per minute, doesn't it? So hours into minutes. 1 hour is equal to 60 minutes. That one is not on the formula sheet because hopefully you know how many minutes in an hour. Anyhow, hours cancels out, so the surviving units are going to be meters per minute, which is what you want. You get your calculator, 50 times 1609 divided by 60. You press the equals button, and well, what it actually gives you is 1340.8 and then a repeating 3, which, as I put on this little yellow sheet here, rounds off to 1340. Another way that gets you the same answer, if you look elsewhere on the formula sheet, it says this many miles per hour equals that many meters per second. And so that would convert miles per hour into meters per second, and then you can convert from seconds into minutes. And that leads you to, many times there is more than one correct way of approaching a problem. So maybe somebody out there even found a third way of doing it. But this idea of canceling units is the point here. Also, this is probably a good time to talk about how to round numbers. I usually start getting questions about that here. It's like, why did you take the 1340.8 and round it off to 1340? Well, flip ahead a page or two, and there's this whole page of single-spaced, densely written stuff about significant figures. And basically what's going on with this is that when I first started doing this many years ago, how to round off the numbers was one of the topics I tried to cover, but it quickly became apparent to me that for people to actually get good at it, I had to have about half an assignment worth of homework problems about that. You know, I had to invest some time in it. And, you know, there's only so many weeks in a semester, and there's only so many topics you can cover. And in the world of priorities, maybe covering conservation of momentum was more important than covering how to round off your numbers. So what I settled into pretty quickly was just writing it all up on a sheet of paper, handing it to everybody and saying, try to do this, okay? I mean, this is the right way to do it, but if you don't, I'm not actually, well, I shouldn't say I won't ever actually penalize you. You've got to draw the line somewhere. And, you know, if the answer is supposed to be 1.47 and you round it off to 1 point, you know, just 1, that's off by 47%. That's a lot. And if you got to draw the line somewhere, and what seems to be a pretty reasonable place to draw it is 2%. So if you are off by less than 2% due to rounding your numbers, once in a while there might be some other mistake you can find that might make you off by less than 2%, and that would be an entirely different thing. But if you're off by 2% or less due to rounding, how you rounded your numbers, I'll just treat it like a spelling error. Physics, F-I-Z-Z-Y-X. If you write that, I may say unflattering things about you where you can't hear me, but I am not actually going to wield the dreaded red pen. Okay. If you are off by more than 2%, I will treat it like an arithmetic error. If, you know, a 10-point quiz and you're working along and you get to this one point here and you say 4 times 3 equals 7. I'm going to look at that and say to myself, I'm pretty sure this person knows that 4 times 3 is 12. 4 plus 3 is 7. They just kind of slipped. I mean, I could have done that. So a little slap on the wrist, half a point off for an arithmetic mistake. And, you get 9.5 out of 10 on that quiz. And being off by, more than 2% due to rounding your numbers, I'm going to treat that like 4 times 3 equals 7. So that's the part that actually influences your grade. The rest of this you should read through and try to remember and avoid looking ignorant. F-I-Z-Z-Y-X. I mean, the reason there's a rule for rounding off, or a couple of rules for how to round off your numbers, is that if you write down 1340.83333, everything that's on your calculator, somebody's going to look at that and say, oh boy, they really measured everything super precisely. No, half of what you wrote down is completely meaningless. Only significant figures should be retained. Figures which are not significant should be rounded away. And not significant means you don't know anything about them, okay? I mean, maybe you weren't driving 50 miles an hour. Maybe you were driving 50.1 miles an hour. How close can you read a speedometer? So in that case, this digit here isn't necessarily a 3. It could be anything. This one here isn't necessarily an 8. It could be anything. The last significant figure is the one that's somewhat but not completely uncertain. So like if this 4 here, I don't know, depending on how far off the speed might be, but let's say this 4 might in fact be a 3 or a 5, but it's not a 9, it's not an 8, it's not a 1. That would be the last one you keep, okay? The last significant figure is the one that's somewhat but not completely uncertain. For purposes of tests and homework and the lecture notes, the standard is going to be 3 significant figures. If I write down 2, that's me being a poor role model. I was being lazy. I meant 2.00. Okay, so for purposes of anything for purposes of any kind of tests, assume the numbers are good to 3 significant figures. In the lab, if you've actually gotten out a micrometer or something and measured to 4 significant figures, then carry 4 significant figures. So enough said about that. Enough time invested in that. Back to this other page. So the current topic is this problem about, we already did that one. Okay. So a couple more comments before I turn you loose on the last 2 sample problems. I have already mentioned how that the directions of your location, your velocity, and your acceleration are all indicated by plus and minus signs. If you're to the right of the origin, x is positive. If you're to the left of the origin, x is negative. For your velocity, if the direction that you're moving is toward the right, v is positive. If the direction that you're moving is toward the left, v is negative, and so on. It's the same sort of thing with acceleration. All 3 of these things are independent of each other, which means just because one of them's positive doesn't mean that the next one is positive. Or if one of them's negative, the next one doesn't have to be negative. For example, and this is another thing that seems to cause people some misunderstanding fairly frequently, so let's take a minute to look at this. Let's say you had a ball and you threw it right straight up in the air. I think it's just coming up next week. We'll see how to deal with it if you throw it at an angle, but for today, you just take it and you throw it right straight up. And it goes up and it comes back down, it drops back into your hands again. So let's look at that at 2 different times. Here it is on the way up. Um, my x-axis, I call it the y-axis if you feel better that way, but I just called it x because it's x in all the equations. My number line, whatever letter I'm using for your position, is vertical this time because it's a ball that's been thrown vertically. The origin on that number line is here where your hands are. Here's the ball, some distance above your hands, and it's going to go up a little higher and then falls back down. And here we look at it at a certain point on the way back down. So, in the first picture, x is positive, assuming that up is positive. It is possible to do a question the other way around if you want to, but assuming that up is positive, then because the ball is above your hands, x is positive. The velocity is positive because it's moving in the positive direction. Okay, it's moving towards higher values of x. But the velocity is decreasing. Remember, acceleration, a, means the rate of change. And with any kind of a rate, increases are positive, decreases are negative. So, you know, it leaves your hand, maybe it's going 20 miles an hour at that point. A little while later, it's going 15 miles an hour. A little while after that, it's going 10 miles an hour, and so on. The velocity is decreasing, which gives you a negative acceleration. So here we are on the way back down in this other picture. X is still positive because it's still above your hands. X would be negative if the ball was down here somewhere. This time, the direction that it's moving is downward rather than upward. That makes the velocity negative. In other words, it's heading towards smaller values of x. X is decreasing rather than increasing. So because x is decreasing, its rate of change, v, is negative. So velocity is positive going up, velocity is negative coming down. Notice that x still has the same sign it did before, but v now has a different sign. X and v are two independent things. Just because one is positive doesn't mean the other one has to be positive. The acceleration is still negative, just like it was on the way up, because the velocity is still decreasing in the sense of becoming more negative. Remember, velocity includes the direction as well as the speed. So even though it's gaining speed, falling faster and faster, when you stick the minus sign on there to include the direction, it's becoming more and more. See, negative 10 is a smaller number than negative 5. If you're playing cards badly, and your score was negative 5, and you do something to lose another 5 points, now you get to negative 10. You lose to get to negative. Or if you're talking about temperatures, if it's 5 degrees below zero, it has to get colder. You have to lose more heat to get to negative 10. So negative 10 is a smaller number than negative 5. As this thing falls, its velocity, at the very top, its velocity passes through zero. And then its velocity is negative 5, and then its velocity is negative 10, and then its velocity is negative 15. Velocity is decreasing. It was decreasing on the way up, which makes acceleration negative. It is also decreasing on the way down, which makes the acceleration still be negative. So once again, A is independent of the other things. Here the velocity is negative and the acceleration is also negative. Here the velocity is positive, but the acceleration is negative. The sign of one has absolutely no influence on what the sign of the other one is. They're independent things. Okay, so that's one point of confusion. Well, it's like, if V is positive, how can A be negative? Well, that's Hopefully I've answered that question. Another common mistake to watch out for is instantaneous and average velocity. Some of those equations had a V average in it. It's like if you're watching a car pull away from a stop sign, when you first look at it, it's going 20 miles an hour. When you quit looking at it, it's going 40 miles an hour. The average velocity during that time is going to be 30 miles an hour, right in the middle, if it's gaining speed at a steady rate. The average velocity is what you get when you, let's back up a page. Let's back up a couple of pages. Back here at the beginning. Distance over time gives you the average velocity. Okay? If you know how far that car went and the time it took to go that far, when you divide them, it gives you the 30 miles an hour, the speed in the middle of the time interval, not the 20 at the beginning or the 40 at the end. People do that all the time. Use a lot of red ink on that one too. So, you've been warned. Okay. So, you should pause it. You should see if you can do number 4. If you get this number here, go on to number 5. If you don't, unpause it and I'll explain how I did it. And if you needed that kind of help, it's probably good for you to pause the recording and try it again. See if you can do it yourself after you've seen me do it. Okay, so I'm assuming you are now unpausing. Number 4. I guess it's centered a little better there. To begin with, and again, I apologize if it's not number 4 in the version of the notes you've got. I'll try and have the up-to-date thing in front of me when I do section 2, but it's, like I said, it's unavailable right now. All I've got here at home with me is the thing I did. All I've got in hard copy form is last year's. So, certain airplane accelerates at 1.25 meters per second. Okay, accelerates, that's kind of a giveaway. A for acceleration, 1.25 meters per second squared. It leaves the ground when it's going 30 meters per second. The faster an airplane goes, the more lift you get on its wings. So that's this particular model. That's the speed you need at the end of the runway. Okay? The process under consideration here is you imagine yourself watching this airplane go down the runway. You start looking at it when it begins to move. You quit looking at it when it leaves the ground. And that's when it's going 30 meters per second. So you can tell it's a velocity by the unit on it, meters per second. If it was acceleration, the time unit would be squared. If it was x, it would just be meters without any time unit under it at all. So the unit, distance over time, that's a unit of velocity, but you've got 3 different velocities in that group of equations. You've got initial, final, and average. Well, this one is the final for the reasons I just mentioned. That's the speed it's going at the end of the time that you're considering. Like I said a few minutes ago, very common mistake for people to mix these different velocities up with each other. So be careful of that. Be sure to stop and think. What's the shortest runway it can use starting from rest? Starting from rest, V initial equals 0. As for what's the shortest runway it can use, that would be the same as the distance moved by the airplane. Delta X is the distance moved by the airplane. Now, if it's got, if the runway is longer, so much the better. But the minimum you can just barely get away with is if the wheels leave the ground just as you run out of pavement. Okay, so The shortest runway would be when the length of the runway is the same as the distance that the airplane moves while it's on the ground. So you got your list, you look at the formula sheet, you try and find an equation containing these four quantities, and this time we get this one. V final squared equals V initial squared plus 2 times A times delta X. The four things in the equation are the four things on my list. 30 for V final, like it says there. The initial, 0. 0 squared is still 0. The acceleration, 1.25. Occasionally, well, maybe more than occasionally, I get somebody that feels they should stick in 9.8 every place they see an A. 9.8 would be the acceleration of this airplane if you picked it up with a crane and then dropped it, okay? But as it is, this is not a freely falling object, and so its acceleration is not 9.8. Rather, as it accelerates horizontally along this runway, this is the rate that its engines make it pick up speed. Delta X is what I want. 30 times 30, 900. 2 times 1 1/4, 2.5. Divide both sides by 2.5. And 360 meters. Okay, if you haven't already done number 5, pause it again. Do number 5. Number 5 is a little trickier. Okay, so we got this one worked out on a different sheet of paper over here. Going about the rock that you throw right straight up at 15 meters per second. Okay, you throw a rock straight up at 15 meters per second as it leaves your hand. So that's the beginning of its flight. That's the initial. How long, meaning how much time until it hits you in the head? So find the time, t. Until it hits you in the head. Now, here's the tricky thing people don't always realize. That is telling you the net displacement, delta x. This, by the way, is not the only way of doing this problem. Many of you may have approached it differently, and if you got the right answer, there's a fairly good chance that was a correct approach, but this is the way I'm going to do it anyhow. One thing I wanted to point out with this example is that delta x does not mean the total distance covered. Okay, how far did it go on the way up? Add that to how far it went on the way back down. That's not the idea. Rather, you've got a number line that the rock is traveling along, and there's the origin there. There is our foolish rock thrower. It's like in all those Western movies where the guys ride into town shooting the bullets straight up in the air. Actually, I heard somewhere that if you shoot it right straight up, that's not quite so dangerous because, you know, the bullet goes up, but once it gets to the top, it starts to tumble. On the way back down, it starts to tumble end over end, and as it chews its way through the atmosphere, it loses a lot of its energy, and doesn't end up coming back down nearly as fast as when you shot it. I guess what's really dangerous is when you shoot the gun at an angle, because then it never stops. It just follows an arc, and it's going probably faster than the speed of sound the whole time. And that's where you get these freak things where somebody's just sitting there in their kitchen sipping tea and a bullet comes in through the window and breaks the teacup in their hand or something like that. Or I guess on a few rare occasions people have been killed that way. But I digress. So X initial is right here. That's where the rock started out. X final is also right here, same place. So whether you call it the origin or whether you call it some other number, X final minus X initial is equal to 0. Because X final equals X initial. Okay, so no net displacement. Once again, displacement does not mean the total distance covered. Displacement means how far is it from where you started to where you end up. And they're both the same place here. And then, like another example I did earlier, even though the question doesn't spell it out, you know the acceleration because it's a free-falling object. Now, plus and minus signs. When I put down a positive, whether I was paying attention to what I was doing or not, whether I noticed or not, when I put down a positive number for V initial, I was assuming up is positive. Since gravitational acceleration is downward, A equals minus G. In other words, negative 9.8 meters per second squared. Minus for down. Now, it's perfectly legitimate to do it the other way around. In fact, if I go back a page, where did I throw that? No, it's a page before that, I guess. Yeah, this one here. How high is the cliff? I didn't stick any minus sign on the 9.8 there. Well, intentionally or unintentionally, I did the problem with down positive. The displacement, delta x, was downward. The acceleration was downward. We didn't get into it in this problem, but any point along the way, the velocity would have been downward. If everything points downward, why not say down is positive and up is negative? And then you don't have a million minus signs to deal with everywhere. So, you know, it's your choice. Once you make a choice, you have to stick with it through the whole problem, but down positive is a legitimate thing to do. But what does matter is whether up is positive or whether down is positive, things in opposite directions have to have opposite signs. If one of these two numbers isn't negative, you're going to get the wrong answer. If you make down positive, then this is negative. Okay, so that's the other trick about this one, is you can't get away with ignoring plus and minus signs. The directions matter. Having done all of that, you pick out an equation containing the four things on the list. Delta x equals v initial t plus 1/2 at squared. And fill in the numbers. 0 equals, initial velocity is 15. Acceleration, negative 9.8. Now, technically this is a quadratic, and you might have to, technically, you know, You'd have to factor it or use the quadratic formula, or, but, you know, there's a shortcut though. What if I divide by t? Of course, that's always tricky because it's extremely illegal to divide by 0, but if you think about it, t represents the time for this rock to go up and come back, and that's going to take some time. That's not going to be 0. So assuming time is not 0, which seems like a pretty good assumption in this case, 0 divided by t is 0. Over here, you know, maybe I should write it all out. 0 over t, 15t over t, yeah, minus 4.9. Half of 9.8 is 4.9. T squared over t. So 0 over t is 0. These t's cancel out, so you've got a 15. One of those t's gets canceled by the one under it. No, that's not so bad. Add that to both sides. Divide. 15 divided by 4.9, 3.06 seconds. Or, you know, you can do it like they taught you in math class where you factor it or use the quadratic formula or whatever. That'll give you the same answer too. As I said, there's other ways of approaching this problem. One popular way to do it is, instead of considering the whole thing up and back, what people will do is consider the one-way trip where it's just going up. V initial equals 0, V final equals 0, or V initial equals 15, V final equals 0. The velocity is 0 when it's up at the top. So you're kind of making an assumption if you do it that way. You're assuming that the time to go up equals the time to come back down. But it happens that that assumption is true. You get away with assuming things this time. So, you know, if based on V final equals 0, you can calculate the time to go one way, and then you can double that, and that gives you the same answer. Like I said, there's different variations. So that mops up the notes for section 1. As I probably said earlier, you need to work on assignment number 1 until you can do it with, you know, right out of your head. And then one of the same, you know, some of the same questions will come back and be the quiz, and you can just do the same thing over again, and that shouldn't be anything to be afraid of. So that's all for now. Over and out.